למה? לא, למה? למי?
זה באמת בעייתי, כן? כלומר, תכלס, הקורס הזה, לפני שנתחיל, הקורס הזה, כן? יש תוכנית בינלאומית עם אוניברסיטאות בסין. אז בפעם הראשונה שהם הגיעו, אז לימדתי את הקורס הזה פעמיים. כלומר, גם באנגלית וגם בעברית, היו שתי קבוצות. באיזשהו שלב החליטו שזה לא טוב לחבר'ה מסין, כי חלק מהדבר הזה זה להיות בהוויית לימודים. כלומר, התרבות הסינית היא מאוד מאוד שונה. לדוגמה, בשנה הראשונה כשלימדתי, זה היה נורא מוזר. הם לא שואלים שאלות, הם ממש בכיתה. זה מאוד לא מכובד לשאול את המרצה שאלה, כי אתה מערער על הסמכות שלו, כן? אז זה היה באיזשהו שלב, אני הבנתי את זה, אז הייתי אומר, טוב, עכשיו אתם תשאלו אותי שאלה. אז הייתי עומד ככה כמה דקות, הם מסתכלים עליי, אני הייתי מסתכל עליהם, ככה זה נמשך. באיזשהו שלב הם הבינו את הטריק, כל פעם שאני עוצר, הם היו שואלים אותי איזו שאלה, וככה היה ממשיך. עכשיו, באיזשהו שלב, במחלקה החלטנו שבסדר, נערבב את כולם ביחד, וזה טוב לסטודנטים הישראלים, שאנחנו גם נעביר את הקורס באנגלית, את הקוד. Okay, אז בדרך כלל זה 7-8 סטודנטים מסין, וככה הכל בסדר. השנה יש רק אחד, כן? זה אמיץ אחד שהגיע באמצע המלחמה לישראל. כנראה שהוא לא קרא חדשות. והמצב קצת משונה, במיוחד שהוא לא מגיע, כן? כאילו, גם ככה אני מרגיש, בשביל סטודנט אחד אני אדבר באנגלית, וכשהוא לא מגיע אני גם ממשיך לדבר באנגלית, שכולכם מדברים בעברית. אז אני טיפה בדילמה, ויש טענה מאוד מאוד חשובה, כן, האם אנחנו נעשה את הסוויצ'ים האלה, כל פעם שהסטודנט מגיע אנחנו נעבור לאנגלית, אז זה קורס כזה חצי באנגלית וחצי בעברית, אז אני לא יודע מה לעשות כל כך. כאילו, זו טענה חשובה, כן, לגבי הרציפות.
אנחנו מעדיפים.
אתם מעדיפים? חצי. אז אני אדבר בעברית ואני גם אתן את כל הטרמינולוגיה גם באנגלית, כדי שיהיה לכם יותר ברור. וננסה לזרום. בואו נראה איך זה מתקדם, מקסימום נחזור בחזרה לאנגלית, אין בעיה. אני רק צריך לעשות את הסוויץ' בראש, ובדרך בניתי את ההרצאה וזה ישב לי באנגלית, אז עכשיו אני צריך לתרגם לי את זה לעברית. אוקיי, ואני לא רואה שהוא מחובר בכלל, זה לא משנה. סבבה, אז מה ראינו שבוע שעבר? בואו נדבר קצת פיזיקה ולא סיפורי סבתא. אז ראינו את החוקים התרמודינמיים. כן? כן.
לגבי האנגלית.
כן.
אם הוא יקרא את ההקלטה הוא לא יבין.
היה שלא. למי מיועדות ההקלטות? בעיקר, מילואימניקים. יש מצב שהוא הולך למילואים? לא נראה לי, כן? לא. אני לא יודע, אולי יש לנו שת"פ עם סין, כן? יכול להיות שיש לנו שת"פ עם סין. אני לא יודע, כן? לך תדע. אבל תכלס, ההקלטות מיועדות לאנשים שמפסידים, זה נכון. אבל עיקר ההקלטות השנה והחובה להקליט, כן? עם כל הסיפורים שזה, החובה להקליט היא עבור המילואים. מי שלא נמצא כי הוא מכל מיני סיבות אחרות, לא בעיה שלנו. חוץ מזה, אני מעביר את הקורס הזה כבר פעם שישית, אני חושב. יש הקלטות באנגלית ובעברית, הקלטות מכל הכיוונים הקליטו אותי. בזום יש הקלטות, מה שאתם רוצים. אוקיי, אז דיברנו על חוקים טרמודינמיים, ובחוקים הטרמודינמיים אנחנו ראינו את הדבר הבא, אז ראינו ש-DE שווה ל-DQ פלוס DW, זה ראינו, זה חוק ראשון. בנוסף, ראינו באיזשהו שלב על ידי זה שאנחנו הגדרנו שיש דבר כזה אנטרופיה, ואנטרופיה היא פונקציה מונוטונית עולה, אוקיי? מונוטונית עולה של אנרגיה. בנוסף, מערכת חייבת לעבור למצב עם מקסימום אנטרופיה, כלומר אם אני מקבל את המערכת, את האנרגיה של המערכת, האנטרופיה חייבת להגיע למקסימום. אנחנו השתמשנו בדבר הזה וקיבלנו גם את הנוסחה הבאה, DE שווה TDS, והיה פה עוד כל מיני דברים, אז נקרא לזה פלוס DW, כאשר DW יש תלוי מה הכוחות המוכללים שיש לנו בתוך המערכת, כן? זה יכול להיות DW שווה למינוס P DV פלוס TDL, תלוי מה הם הקורדינטות שאני מדבר עליהן, ומה הם הכוחות המוכללים. הכוחות המוכללים זה לחץ, טמפרטורה, הקורדינטות המוכללות נפח, אורך וכו' וכו' וכו'. בנוסף, אוקיי, אני רוצה להגדיר עוד משהו, כן, לגבי הכוחות המוכללים שלנו, כן? אז P לחץ כוח מוכלל. T, מתיחות, כוח מוכלל. ואני רוצה לדבר על עוד משהו, כן? מיו, שזה פוטנציאל כימי, או chemical potential. פוטנציאל, אוקיי? מה זה הפוטנציאל הכימי? הפוטנציאל הכימי זה גם כוח מוכלל. הפכתי לכיוון. כוח מוכלל. מה זה הפוטנציאל הכימי? תשימו לב, זה אנחנו כרגע מדברים על יצור מתמטי שאנחנו קראנו לו באות, סימנו אותו באות מיו, אבל תשימו לב, כשאני מדבר על כוחות מוכללים שאני ממציא, שאני שם אותם כאן ואני שם אותם כאן, איך אני מגדיר את הכוחות המוכללים האלה? קואורדינטות זה משהו שמגדיר את גודל המערכת, אלה גדלים אקסטנסיביים. אז בעצם, מהנוסחה הזאת, כן, אני יודע, כן, אם נרשום את זה, DE שווה ל-TDS מינוס PDV פלוס, זה יהיה טאו DL. כן? אז מה שאנחנו יודעים זה את הדבר הבא. הנגזרת, האות שעומדת כאן לפני ה-DS, כן? זה פשוט DE, דו E לדו S, DS, פלוס דו E לדו V, כן? היי! Okay, we're switching back to English. So this is the differential of the energy. We were hoping that you won't come, so we can speak in Hebrew. Don't worry. So this is the differential of the energy. Okay? This is the differential of the energy. And all the partial derivatives that stand in front of the differentials that are associated with extensive variables, entropy is extensive, volume is extensive, linear size of the system, the length of the system is extensive. So what we have here is dE to dl, all of those guys are generalized forces. Now I told you that there is an additional generalized force that I want to introduce, which is mu chemical potential. Okay, so this is pressure, this is tension, this is generalized force. Generalized force. Okay. I want to introduce an additional generalized force. Why do I want to introduce it? Because when I'm describing my system, I'm not only using as extensive variables the entropy, which I don't really understand what it is right now. I have some mathematical properties, but I haven't explained it to you yet. I understand what is volume, I understand what is length, but there are also an additional coordinate, extensive coordinate, which is n, the number of particles in the system. N, number of particles in the system. Okay. It is extensive quantity, right? If I have two subsystems, I add them together, the total number of particles is going to be just a sum of the number of particles in system A and the number of particles in system B. So this is extensive quantity. Extensive. Therefore, when I'm writing my dE, I should write dE to ds plus dE to dv plus dE to dl and plus dE to dn. So there is an additional generalized force, which is a partial derivative of the energy with respect to the number of particles. Right? And I call this generalized force chemical potential. So dE to dN equals mu chemical potential. What it means, exactly what is written in this equation. Chemical potential describes to us by how much the energy of the system is going to be to grow or decrease if I modify the number of particles inside my system. That's it. Okay, so this is a very clear mathematical definition. In general, n is the total number of particles, right? But we can go even further and say, well, why should I care only by just the total number of particles? I can say that the only thing that the particles are different. Okay, so it's not just like blue balls inside my system. I can have blue balls, red balls, some other structures that are wandering inside the system. So in general, I say that the energy of the system depends on the entropy, it depends on volume, it depends on, can be dependent on length. And instead of just saying that here I have the total number of particles, I can have total number of particles of type 1, total number of particles of type 2, total number of particles of type 3, etc., etc., etc. So this is particles of type 1, and this is particles type 2, and etc., etc., etc. So usually we won't care about we won't deal with systems that have different particles or different types of particles. Okay, but in general there are situations when we are dealing with many constitutional systems. So can be, for example, different types of molecules. Right. So any solution, there are molecules of type A, molecules of type B, molecules of type C, whatever. For each of those molecules, I can define a chemical potential, right? So here, mu1 is going to be dE to dN1, and mu2 is going to be dE to dN2, and etc., etc., etc. So I can define chemical potential for all the different types of molecules that I have inside a system. Right? I'm just using this definition. By how much the energy is going to be increased or decreased when I change the number of molecules, total number of molecules, or very specific type of molecules. Okay, so we won't deal a lot with many types of particles. For now, let's concentrate on the following thing. S, dl, and n. So this is the system. We have a general system. This is the energy of the system. The energy of the system, as we already shown, depends on the entropy, volume, length, number of particles. Great. But what is entropy, right? So I'm talking, it's already the third lecture. We started our first lecture somewhere over there. Well, we have entropy and we define entropy, that there is some function, but don't really understand what entropy is. Okay. Moreover, the basic variational principle that we imposed on any thermodynamical system was what? That in equilibrium, any system should have a maximal entropy. Right? Afterwards, we derived that there should be minimal energy, and etc., etc., etc. But the basic principle was maximal entropy. But we don't know what this entropy is. Now, moreover, although I'm a theoretician, from time to time I have to speak to experimentalists. And now, let's assume, pick up some experimentalist of our department. Let's call it Eli Slutskin, right? You all know Eli Slutskin. I'm coming to Eli Slutskin and we're talking about an experiment. And I say, Eli, you have to modify the entropy. Okay? You have to modify an entropy to see this effect. Now he will look at me and say, how do I modify entropy? What are you talking about? There is no way, I don't have something that modifies or even measures entropy in my lab. Right? So people usually do not play with entropy. So what is entropy is associated with? See it over here, right? So entropy is somehow associated with temperature. Now temperature, well, although it's something which is much more common, right? In every house we have a thermometer. We can know how to measure entropy. Okay? There are procedures, etc., etc. It's experimentally not so difficult to measure entropy. Okay? So what I'm saying is this is nice to have energy, because if I know energy, I can derive everything, right? But it's nice to know energy as a function of entropy. Well, I can modify volume, I can modify the length of the system, I can modify the number of particles, I can control. Those are control parameters that I can play with. Entropy, not so much, right? I cannot really measure entropy, I cannot play with entropy, but I can do something with temperature. Okay? I can do something with temperature. So the idea, the following idea is, in order for us, or for all this theory to be applicable, not just mathematically reasonable, but actually applicable, it should have some specific predictions. Those predictions can be measured in a lab. We do not want to describe everything in terms of entropy, but somehow we want to describe everything in terms of temperature. So this is our goal. So what we want to say, all right, I want to go to describe the energy, not in terms of entropy, but in terms of temperature. Okay, so how do we do it? And what exactly is the idea? Okay, so what we are doing now, transition S to T. Think about the question in geometrical way. I have coordinates in my system. The coordinates are entropy, volume, length, n. We can forget about all those three because I'm not going to modify it. And I want to express everything in terms of a new coordinate that I call temperature. The people who studied analytical mechanics, you've seen this procedure before, right? Legendre transformations. Okay. So in analytical mechanics, when you have some Lagrangian or Hamiltonian that is described by some specific variables, there is always a transformation to conjugate variables that can make your life simpler. The same idea is going on over here. I have some specific variables, let's forget about those. I have, and this is my variable. I don't want to work with entropy because I don't know how to modify it. I want to work with some another quantity t. Why I have chosen t? Because it's a conjugated variable to s. Okay? And we'll see how exactly it is achieved. But what I'm going to describe to you is Legendre transformation. Legendre transformation sounds like, wow, Legendre transformation, but it's just a French guy who died a long time ago, and he had a very simple idea. When we have a function, our function is e and our coordinate is s. So that's what we have. So let's assume that this function behaves like this. Okay? Now, I don't want to describe E in terms of S, right? I want to describe E in terms of some other variable. This variable is temperature. Why temperature? What exactly is temperature? What is T? What is T? Do you remember what is T? Derivative of E with respect to S. dE to ds. So temperature is the slope if I will construct a straight line in some specific place. Okay, so this is E, this is S, and I construct a straight line that is adjacent to my curve in some specific point. So what I'm saying to you right now, that I want to describe E in terms of local derivatives of this function. Not with respect to S, but with respect to local derivative. Is it enough just to know the derivative of the function in order to describe it?
No.
No. No. We need, so it's like a derivative is not enough. If you remember differential equations, if I have differential equation of the first order, in order to solve it, I don't need to know what's the derivative. I need to know what the derivative is and the initial conditions. Right? So for my case, what I want to say is, in order to describe properly E, I don't need just the slope of this straight line. I also need another point. And Legendre have chosen the point when this straight line crosses E. Right. Let's call this point F. Okay. The idea of Legendre is very simple. He said the following thing. There is a connection between F, E, S, and T. This is the derivative. What is the connection between the four?
E minus ts.
T equals to E minus F divided by S. S minus 0. Okay. Fine with you? Is this the right connection? This is the slope. How I calculate the slope? Delta y divided by delta x. Okay? So this is the derivative. This is going to be tangents alpha, and tangent alpha is just the derivative. Okay? Great. For any different point, there are going to be different temperature. All right. So what we are doing from here, so Ts equals to E minus F, or F equals to E to the minus Ts. Legendre says, hooray, in French. This is my transformation. Legendre transformation. You can say, well, hold on. No. The idea was, what was the idea? To describe energy, not in terms of entropy, but in terms of temperature or some other variable which is controllable. Well, you have done something over here. First, you created a different function. B, who says that this new function is indeed depends on temperature and not on entropy. How do we show this? Derivative. We take a differential of f. So if we say the following thing, let's take differential of f. What is the differential of f? The differential of f is the differential of E minus Ts. Okay, so let's see where Legendre takes us. So it's the differential of E minus the differential of Ts. Okay? Which is the differential of E, what it is?
0.
Oh.
No, we already know that.
If E is function of S, this means that dE is TdS, right? We know this.
Yeah.
Okay. So what we have here is TdS minus, this is the differential of multiplication of two functions. So it is minus S dt minus T ds. So we can kill, what we can kill, this and this. What we have obtained is that if f is E minus Ts, this is our Legendre transformation, which is based on an attempt to describe E in terms of its derivatives, df is minus s dt. Okay? So on the left-hand side, we have the differential of the function. On the right-hand side, we have a differential of the variable on which this function depends. So what we can say is that f is a function of t and not of s. So the true variable that describes this function f is not entropy anymore, it's temperature. How this function is called?
Free energy.
This is free energy. So f, which is E minus Ts, it's called Helmholtz free energy. What do I mean by free energy? So first of all, I made one single transformation. I haven't modified all the other variables that define E. So f is going to be dependent on t. All the other variables, what are they? Volume, length, number of particles, stayed unmodified. Why they stayed unmodified? I could add them over here, right? I could add them minus p dv plus tau dl plus mu dn. Everything stays the same. The only thing that this Legendre transformation, this specific Legendre transformation does, it kills this variable s. And instead of s, we have a variable t. So f is a function of temperature, volume, length, and the number of particles that we have inside us. So now, when I'm talking to my favorite experimentalist, I won't tell you who he is or she. I'm going to describe everything. If I want to speak to them and I know that they have thermometer in their lab, I'm going to try and present everything not in terms of energy, but in terms of free energy. Helmholtz free energy. Why? Well, because there is temperature and they can control temperature. Now, the Legendre transformation is very, very general. In mathematics, everything works like that. You have a very simple idea. It's usually a very, very simple idea that you can describe simply, and then you can say, well, it actually holds for very, very general setup. So you don't have to have only two coordinates. You can have as many coordinates as you wish, and this Legendre transformation will still hold. How it's exactly proved? In the same fashion as I did to you for this simple example. So let us write down the Legendre transformation, a general Legendre transformation. Legendre transformation. So if I have a function which is a function of x0, x1, and xt, so those are the coordinates of my system. I want to describe another function in the following way. I have y minus a sum that starts from j up to t of pk xk. So what are those pk's? Pk's are the partial derivatives of the original function with respect to the original derivatives. dy dxk. Conjugated variables. Hooray. So we know that psi is a function of x0, x1, x2 up to xj minus 1, and here I will have pj plus 1 till pt. So I swapped all the originals from xj to xt to new variables pj up to pt, And this new function, psi, is not a function of all the x's, but it's partially a function of x's and partially a function of p's. And it depends on what exactly I subtracted over here. Okay? And in general, d psi to dpk equals to minus xk. You can always see it over here. df to dt equals to minus s. All right, so by this Legendre transformation, I can create different functions, right? Because in energy, I don't like the looks of the entropy. So I swapped it and I obtained Helmholtz free energy, right? So we don't like entropy, so let's get rid of it and let's describe everything in terms of entropy. Okay, so this is the first one that we derived. Okay, so F equals E minus Ts. I switched S, so S is a function of T, V, L, N. Okay, let's assume that I don't like. Yes.
אי אנחנו מבינים מה זה, הכרנו כבר, מה זה אנרגיה.
Yes.
מה זה F?
So the question is, I know what is energy, because you're used to energy, right? I'm telling you now, forget about energy, let's use free energy. Okay? So what is free energy? It's a type of energetic potential that have different coordinates than energy. That's it. It's a mathematical way to describe something in more convenient way. What I can tell you that it's the same as energy, but described with different variables. That's it. Okay? Yes. Sure. You will see examples of van der Waals gas or free energy or free gas, and you can see that actually I can derive the free energy of the gas and I can go and measure it. Sure. And it's controllable. Why is it controllable? Because there is temperature. I can modify the temperature in the system, right? I can heat it up, I can cool it down a little bit, I can measure the temperature, I can say, oh, now the temperature is 30 Celsius. And I can go and measure it. Now, moreover, we will see towards the end of the class that almost everything will be described less in terms of energies, but actually in terms of free energies and other types of thermodynamic potentials. So all those guys, they have a name. Thermodynamics potentials. Thermodynamic potentials. Okay. Why potentials? Because I don't like energy because I don't like entropy. For example, I have Helmholtz free energy. Helmholtz free energy. Okay, so let's assume that I don't like what I don't like. Many stuff that I don't like, but I don't like entropy and I don't like volume. I don't like volume. Why? Because I can control something else. So we can have the following thing. Okay, so I don't want entropy. I'm going to describe everything in terms of temperature. But I also told you that I don't like volume. So I don't want to get rid of the volume. What is the conjugated variable that associated with volume? Pressure. Okay, but we have not pressure, we have minus pressure. Okay, so I minus whatever stands my general coordinate, my general force, which is minus P multiplied by V. Okay, and G, according to the Legendre transformation, instead of S we have T. Instead of V we have P. We have tau and we have n. This guy is called Gibbs free energy.
Why would we have tau instead of L?
Oh, you're right. I'm sloppy. Okay, and what else can we don't like?
Stat.
Yes.
What if we calculate the conjugate of P in the F world? Like if we take the
But P said, so this is exactly this. This is Gibbs. If you take F and subtract from S PV, this is exactly Gibbs.
Yeah, but the conjugate of P in F is not exactly
The same. It's the same because F depends on V, and the conjugate of V doesn't really matter where, is always P.
Okay.
Okay?
Why minus P?
Because if you remember, dE was what? TdS minus P dV. So because of that, we have minus P over here. It's going to be minus whatever stands in front of the coordinate. That's how this Legendre transformation works. Okay, so let's write. We are two thermodynamic potentials left. So this is, if I don't like, I like entropy, right? I like entropy, but I don't like volume. So this is H, which is E minus P V. Okay? And H is a function of S, P, L, and N. So this is enthalpy. Okay. And last but not least, grand canonical potential, which is, I don't like entropy, and I don't like the number of particles that I have inside the system. You can say, well, but why? Right? Number of particles is something good, you can control it, you can count them. But you will see that there are a lot of systems that the natural coordinates is not number of particles, but the chemical potential. So this is mu n. And psi is a function of T, V, L, and mu. So this is grand canonical potential. Okay. All of them are potentials, thermodynamical potentials. As I already answered, we use them because sometimes we prefer to use different coordinates and not the coordinates that are associated with energy. Sometimes it's simpler because of the experimentalist. But in most cases, it's simpler for the theoretician to describe the system by using different coordinates. You've seen this in analytical mechanics. You just use a different geometry to describe the same system, and sometimes everything is so simple, right? There's even this Hamilton-Jacobi theory that you can always have some specific geometry where everything is particle without forces or particle with harmonic potential. So it can be very crazy coordinate, but it should exist over there. The same idea holds over here. You have potential, everything is described by this potential, you have to find a minimum of this potential, right? Because the system in equilibrium is going to be at minimal point of the energy. Now, sometimes you don't want to search for something minimum of the energy, you want to use different coordinates. That's why we have this thermodynamical potentials. Now, and this is very strong claim. Variational principles. I won't prove it to you, but the proof is very similar to the proof of why energy is minimal at equilibrium. All the thermodynamical potentials are at minimum, or have minimum value, have minimal value at equilibrium. So this is very strong, right? So we don't have to search only for the minimal value of the energy. If we prefer to work with other coordinates, we can search for the minimal value of free energy, or Gibbs, or enthalpy, or the grand canonical. It doesn't matter. It's still described as the system, maybe with some other coordinates, but the point of equilibrium is not going to be modified because we have chosen different way to describe it. It's the same point. Alright, we will stop here, and tomorrow we will continue to what actually we can make with those potentials to stabilize systems. See you all tomorrow. כן. F.